Hi, my name is Mack Gregory, and today I'm talking about improving the efficiency and accuracy of hybrid finite element and particle and cell methods for modeling geologic processes in the Earth's interior. The motivation behind my research is to help model the movement of tectonic plates and other currents, conduction, and movement in the mantle. So on the left, we see a simplified model of tectonic plates where we have a subduction zone where a slab is going under another slab that causes earthquakes, and this is where we want to research that we can have better understanding of how these events happen. On the right, we see a slice taken out of a 3D model done with particles. We have different colors on those particles representing where they're from. So we have brown particles that come from the core mantle boundary, but we also have red particles that have come from the surface. One of the first models that had started to try to accomplish these models is the sinking block benchmark, first studied in 2003 by Gurria. It's an idealized model of subduction and the other involved processes. Its entire computation is that initially a square dense block falls in a less dense medium. And this shows how down this line in the middle, I'm going to use my laser pointer thing here, we have this area that there's not any particles. And that is bad for the many different interpolation methods' accuracy. On the right, we show the grid size for this computation and how using an adaptively refinable grid, we're able to save computational power for where it's needed most. Through aspect, we approximate the solutions to the incompressible Stokes equations, where we have U as the velocity, P the pressure, rho density, and G for the gravity vector. We try to compute approximate solutions potentially or aspect computes approximate solutions for velocity, pressure, and density using finite element methods based on the grid size. Our finite element can be coupled to particles with aspect, each of which can carry some physical quantity such as density or viscoplastic strain. Our goal is to approximate the true solution, such as for velocity, as close as we possibly can. And how we measure this as close as we possibly can factor of it is through the convergence of the method, which is a fancy way of saying how the approximate solution approaches the true solution as the grid cell or grid size approaches 0. So what we do is we take the norm of the difference between our approximate solution and actual solution, and then compare it to the grid size to the Q power. And then we would call Q the order of accuracy of that method. So if Q is 2, then every time we half the grid size, we'd expect the error to decrease by a factor of 4. Here we have a test problem that we've made to verify the accuracy of our biquadratic interpolation algorithm, as well as bilinear interpolation in 3D. We wanted to check both of them. So here we show a model that starts with a compositional field denoted in red in the bottom corner here, and in the area that does not have that composition shown in blue. If I click play on this, you can sort of see how the composition moves throughout the model. And what this does really is it shows how aspect is tested and verified to make sure that it's correct. Anytime that anybody would like to change aspect in any way, their change has to be vetted by several maintainers of the aspect program, who then make sure to test it against hundreds of hundreds of test cases, just like this one, to make sure that the output does not change unless it should and is meant to. It protects the accuracy and stability of the program over time. Here we have the rigid flow benchmark. It checks the accuracy of the aspect over time and makes sure that how a new model, a new computational method works. What's great about this is something to verify particle computations is that in the corners of this picture at the bottom left, we have areas where particles are not present, which we can see with white, where we have lines of colored particles that show where they initially were, but these particles are moving away from each other and towards the middle, and that leaves areas with inaccurate results due to how few particles are left in those areas, as they try to interpolate the density and other physical quantities with the finite element methods. Here we show that with bilinear and the direct method, methods that already existed prior to any of my research, how with SOLKZ there's already second and third order accuracy with particles. However, the third order accuracy with bilinear depends on having 4096 or other similarly and unreasonably large numbers of particles. And having that many particles, it's somewhat reasonable when you only have h being 1/8, but by the time that h is more like 1/100th or so, then it's much less reasonable to have so many particles in your model overall. We also have the direct method here that has fourth order accuracy, showing that there is room for growth from bilinear. Here though we switch over to having fourth order accuracy, and we do it with a constant 9 particles per cell. And that means that we're able to get to 10 to the minus 12th in our error, which is getting close enough to floating point that we don't typically test beyond that. For Q3, Q2, again, here we're comparing them on the same graph, but I've moved some of the particle per cell numbers around. So we have second order particle per cell of 16 with bilinear. We have 6,400 particles per cell with bilinear, getting fourth order accuracy here on rigid shear as a time-dependent benchmark. And we also have 25 particles per cell biquadratic that gets fourth order accuracy, and the direct method that gets fourth order accuracy. So biquadratic isn't alone right now, but it is alone as far as a low number of particles is shown. There's not competition as far as we know that allows you to have fourth order accuracy on this kind of modeling while still using particles and not having an immense number of them. So what is our biquadratic interpolation algorithm, and what does it compare to of this bilinear that I've been calling it? Biquadratic, as we've been calling it, at least in 2D, is shown with the following terms with their own coefficient c. So we have one term, we have an x term, a y, an x squared, and an xy, and a y squared for our biquadratic. We are still doing some work with this to figure out if that's all we really do need, or if we should include more terms for some models that we haven't tested yet. There's always more models that might benefit, and being least squares, it should not hurt the accuracy if we continue adding new or more terms into our equation, as long as we don't just push it so far that you need more particles to make the matrix A overdetermined. Here we go into some of the references. I'd like to personally thank my mentor, Professor Puckett, who's a co-author on 2 of these, along with some of the maintainers of Aspect, especially Renee Gizmoller, for all their work in supporting me through this and helping me. And I'd also need to reference Gerry at UN and their initial work with the sinking block. Thank you so much for your time, and please leave any questions that you have in the comments area for this below. Thank you.